Here, how to determine the ripple factor in single phase diode bridge rectifier by using PSpice. Okay, so we have to verify the practically by using PSpice software. So determine the by determining the ripple factor with filter and without filter. Bridge rectifier circuit without and with filter. So in this, we have to construct the full wave bridge rectifier circuit and analyze the its outputs. Okay, and also rectifier output using capacitor in shunt as a filter. Shunt filter, capacitor using as a filter. So in this, this is called a single phase full wave bridge rectifier without filter resistive load for R load. Okay, and these are the working principles you know well. So then VDC is equal to 2 V maximum pi that is equal to 0.637 V max, and the ripple factor is defined as a VAC by VDC, average value of output voltage by average value of VAC by VDC, that is called. So it can be written as VRMS square minus VDC squared by VDC. So 100 of VRMS by VDC whole square minus 1. So in this way we have to find the ripple factor of a single phase diode bridge rectifier. Okay. So ideally, so we will get 0.48%, 48% of single phase diode bridge rectifier. Okay. And here the ripple frequency is now twice the supply frequency. For example, 100 frequency, then if supply frequency is 50 Hz, then ripple frequency is called 100. It's two times, twice the supply frequency. The supply frequency is 1 kHz, ripple frequency 2 kHz, like this we will. Okay. And rectification efficiency, that is equal to output by input VDC into IDC divided by VAC into IAC. Output by input is called rectification efficiency. So power loss, if any power loss are there, efficiency decreases. So power loss is nothing but VDC squared divided by RL divided by VAC squared divided by RD plus RL. So by substituting this all values, then you will get like this. And then this is about without filter, and then with filter, this is the circuit diagram. Single phase diode bridge rectifier with filter. So by using the filter, this ripples across the load is decreases. Output waveform, in the output waveform across the load, the ripples are decreasing. So this ripples reduces because of capacitor filter. So capacitor not allow sudden changes in voltage, that is called spikes. Ripples cannot allow capacitor. So then the output voltage waveform, output voltage will become smooth. Okay, here in this region capacitor charges, and then next rigid charges. So up to here this is called charges, discharges, charging, discharging, like this capacitor charging, discharging. Okay, and that means capacitors not allow sudden changes in voltages, that is called ripples, is not allow sudden changes in ripples. Okay, so in this way the capacitor control the ripples. Okay, so by using the filter, so we have to reduce the ripples. Okay, ripple factor is less and with capacitor. Uh, so then observations. Then we have to observe the input voltage VAC. Okay, first we have to take the readings like this in full wave rectifier without filter. Load resistance. So we have to fill the details. This load resistance RL and input current IAC milliamps. Output voltage VAC and VDC, average output voltage VDC, and also VRMS we have to determine by using PSpice software, and 2V maximum by pi we have to find. Ripple factor, that is called R, under root of VRMS by VDC whole square minus 1, and efficiency, rectification efficiency. So by using this formula, so we have to find and then fill this table. Next, similarly, so table 2 with filter, capacitor filter, this is called capacitance value, C is equal to microfarads. So in the range of microfarads. So load resistance RL same as previous one, and then output voltage VAC in volts and VDC in volts and ripple factor. So like this we have to execute and we have to fill the details. Okay, so by using PSpice. So this is the schematic. By using PSpice we have to design like this. This is called sine input, and amplitude is called 50 and frequency 1 kHz, and so we have to enters like this. AC is equal to 0, DC is equal to 0, amplitude is equal to 50, and frequency 1 kHz. Okay. And like this we have to connect bridge rectifier. Then the voltage across the resistor is called output voltage. And with this is called without filter. Without filter, we have to execute this experiment and then simulate. Then we will get output voltage across the load. So load voltage. So load is connected between this 1 and 2. So load is connected between 1 and 2 terminals. Am I right? The voltage marker is connected at input side, and also the one voltage marker is connected across the resistor. Voltage difference. Pluses and minus voltage difference marker. And here, so input side voltage marker red color and yellow color. Then so the pop-up is appear like this. This is our output voltage waveform, full wave rectifier output voltage waveform, orange color, and the red color is called our input voltage waveform. So in this way we have to execute this experiment, and then after executing the experiment, first we have to find the VDC and the VAC. VDC, first we have to find VDC, average value of output voltage, and then next RMS value of output voltage. So remove this and then go to trace, add trace. So right here expression average, the load is connected between 1 and 2. Okay, here 1 and 2, that's why uh, we average of v of 1 comma 2, right? Like this expression v of 1 comma 2. So this is called our average output voltage. Average output voltage. Change the width of this waveform. So this is our average output voltage, approximately 30 volts. Okay. So enable toggle cursor and place here and mark label. So 30 volts, 30.508. This is called our average output voltage. Okay. And then similarly, so go to trace, add a trace, and similarly RMS value. Average value is completed. Then RMS value of V of 1 comma 2, because of load is connected between 1 and 2. V of 1 comma 2. Okay. So this is our red color is called, the red color one is called width, change the width is called RMS value. So the RMS value is nothing but here, select here. The RMS value is approximately, so here that 30, 40. That means maybe 33 or 35 in between these two. Here, middle 35. Okay. This RMS value is 35, average value 30. Okay. RMS value and average value. So like this, we have to find RMS value, average value, and then we have to substitute in this formula VRMS by VDC in this formula. So then we will get ripple factor. Ripple factor without filter. So VRMS 30 divided by 35 under root of VRMS is called 30 by 35. 35 by 30. VRMS is called 35 and VDC is called 30. And then we have to find ripple factor. Okay. Values here. VRMS is equal to, then our practical by executing this experiment, so we are getting some values now. VRMS is equal to 30, V average is equal to 35, VRMS is equal to 35, V average is equal to 30. By substituting these values, so we will get a ripple factor is equal to 60%. Okay, so this is about without filter. So these are the ripples, and ripples is equal to 60% are present in this output voltage waveform. Okay, so then we have to execute this experiment by using capacitor, by connecting the one capacitor across the send of load. Okay, so go to schematic, close this output waveforms and go to schematic, and then take one capacitor, connect across the load in the range of microfarads. Then we have to check how ripples are changes. Change this my nanofarad to microfarads. For example, microfarads. For example, 100 microfarads. doesn't take 100 microfarads. And then this is our input, this is our output, voltage across the load. Similarly, voltage across the load is nothing but voltage across the capacitor. And the simulate. So on this way we will get the voltage, input voltage waveform. This is our input voltage waveform. So based on the capacitance, the average ripples are reduces. If high values of capacitance, we will get exactly DC. So in this way we will get up to here the capacitor, this charging and then discharging, charging, discharging. So like this with filter. So capacitor here to charging and then discharging, charging, discharging. So for example, I'm reducing the capacitance to 100 microfarad. I'm reducing the 10 microfarads. For example, I'm introducing capacitance 10 microfarads. Then so like this, the waveform. If capacitance is more and then ripples are less. Capacitance is less, ripples are more. Okay. So this is our input voltage waveform. This is called voltage across the load capacitor. The capacitance value is less, no? 10 microfarads. That's why. So we are getting the more ripples. So up to here, this is called capacitor. Exponential is increasing means capacitor charging and then discharging, charging, discharging. Same as this in this waveform. Resultant output voltage with capacitor here is increasing and decreasing, charging and then discharging, charging, discharging. So like this, output voltage changes across the load with capacitor. Okay, and then next. This way we have to execute this by using capacitor, and then next we have to determine average value and average value. So VDC VS. Okay, so VRMS by VDC. Under root of VRMS by VDC whole square minus 1. Triple factor we have to find. So that's why we need average value of DC output voltage and RMS value of DC output. So load is connected between 1 and 2. That's why. So average, take average of V of 1 comma 2. Right here expression like this. We have 1 comma 2. So this is our average value 40 volts with capacitor. So average value is called 40 with capacitance. Like this we will get. And then similarly take RMS value. Write the expression, go to trace and add trace and write here RMS of 4. So right side the expression is there available. So RMS of V of 1 comma 2. The load is connected between 1 and 2. That's why we have to write in this way. So this is also, this is called, red color is called RMS value. So by looking this waveforms, we can understand this RMS value, average value almost near. That means ripples are reduced. Okay, average value and RMS values are very near. Average value is called 40 and RMS value is maybe 42. Near to average value. So average value is called 40 here. The green color line is called average and red color line is called RMS. Here average value is called 40, then RMS is called 42. Okay. So then substitute these values in this ripple factor formula. So here 42. 42 is called RMS value. Substitute this and then you will get so under root of 42 square divided by 40 square. 40 square minus 1. Then you will get like this. Minus 1 means here 320 into 10 to the power minus 3 into 100. Then if you want to get a percentage into 100 and then 32%. So VRMS by VDC whole square minus 1 you will get 32%. Okay. Previous 60, approximately 68% without filter. Then with filter, the ripples are reduced to 32%. Almost 50% is reducing by introducing capacitor. Okay. So like this, we have to execute and we have to find the filters, ripple factors by using filter by using this formula VRMS by VDC whole square minus 1. And then we have to reduce the ripples in output voltage waveform by adding capacitor filter. This is about single phase diode bridge rectifier. Similarly, three phase diode bridge rectifier also. So by connecting the capacitor across the load, and then we have to how the ripples are changing by connecting capacitor across the load. How ripples are changing, we have to identify. Okay, definitely by adding the capacitor, ripples is reduces. How much it reduces based on capacitance value. Here, capacitance by increasing the capacitance value, and then average. For example, here increase capacitance value is equal to 100 microfarad. Okay, and then simulate again. So by simulating this, this is called our input waveform. This color is called our input waveform, and this orange color is called output waveform. In this output voltage waveform, approximately DC. So only small ripples present in the output voltage waveform. Okay, by increasing the capacitance, that means we will get exactly DC voltage by introducing capacitor. Okay, for example, so we have to check the average value and average value by increasing the capacitor. Go to trace and add trace, and write here expression average of V of 1 comma 2. The load is connected between 1 and 2 now. That's why write like this. And this is the initial, but finally there is no ripples. Without ripples, we are getting the output voltage DC output voltage. Okay. Go to properties and width, change width. And this is called without ripples, we are getting the voltage output voltage waveform, average output voltage. Okay. So this is across the capacitor. By using capacitor, we have to get like this average one. Similarly, RMS value also. So go to trace and add trace. Go to trace, add trace, and RMS. RMS of V of 1 comma 2. V of 1 comma 2. Right, like this. So these are our entries called properties. Go to properties. This called RMS value. So this way we have to execute. So by adding the capacitor, by increasing the capacitor, the ripples are almost reduced to very less. Okay, almost RMS value, average values are equal, approximately equal. Okay, so this is about the single phase diode.